All right. So last week we have looked at the combinational logic or combinational circuit design. So today we will continue what we have done, and we expect that today we will complete chapter 3. So we have looked at decoder, multiplexer, magnitude comparator already, and adder, also subtractor and sign number. So last week we have extra tutorial also on designing adder subtractor circuit. So I hope that tutorial will help you to understand the subject better. And today we will look at um, the comparator, actually another kind of comparator, which is the arithmetic comparator, which is the one that we use in digital system actually, especially in the computer, microprocessor, and so on. And last part is the multiplier and the yes, we have actually arithmetic comparator. We will look also at the multiplier and also the ELU. So we will look at these three today. So let's go to that part. Operator done. Adder done. So we have learned how to design an adder, an n-bit adder, so more than 1 bit adder, using hierarchical modular design or hierarchical design methodology. Sign number, we have learned what is the number that we represent in digital. So we represent the number in digital using two's complement, two's complement number for the negative number. Right? So that's because we will use the adder to do the subtraction. All right. Okay, so last week, yeah, we have this tutorial and we have designed the circuit using Verilog and simulate already. Now today we will look at what is called an arithmetic overflow. The arithmetic overflow, what is that? So when we look at our system in digital system, so we will need or to know the size of our system or our data, our number. All right, and because we want to process or to store the data in the hardware, and the hardware is actually limited. For example, if our size of the adder is 4 bit, so the number that we can process or the number that we can manipulate is 4 bit only. All right. So what if, for example, if we look at this table, all right, this is the number representation of digital domain. So for example, number 4-bit system, 4-bit system. So remember that we use two's complement or second complement in digital system. So we can see that the maximum number that we can store for the 4-bit system for the positive number is positive 7. Means that positive 8, positive 8, we cannot store in the 4-bit system already. Because when we look at 8 in digital, let's use this so that I can share this share the screen. All right, so when we look at this, yeah, so the maximum value is positive 7. So the next value should be positive 8. All right. So 8 in digital is 1000. Okay. So 10000, when we look at the sign bit, now the MSB is sign bit. All right. So this indicate that this is negative number actually. All right. So we cannot use 1000 to represent 8 in 4-bit system. So if we look at this in this table, yeah, here 1000 is actually minus 8 in digital system, and minus 8. So we cannot store positive 8 in 4-bit system. All right. Also, when for negative number and negative part, positive we have 0 to 7. Negative part we have minus 1, and the smallest is minus 8. All right. So what about minus 9? So also minus 9 cannot be stored in 4-bit system. All right. There is no space there to store a minus 9 or positive 8 or positive 9 and so on. All right. So when we have an arithmetic operation, for example, a plus b, and a is 5 and b is 3, so the answer is 8, right? Positive 8. So this 8 cannot be stored in a 4-bit system. So this we call arithmetic overflow. Okay, so arithmetic overflow is simply when we do the arithmetic operation on any operand or number, all right, and the result is not fit in our system. If we use 4 bit, for example, our result is more than 7 or less than minus 8, so that we call arithmetic overflow occur, or arithmetic overflow happen. All right. So when we design a digital system, we need to have a mechanism to check that arithmetic overflow, so that we can handle the number, all right, or the result. So for example, our system is 4-bit, and so when we do arithmetic operation, we not only want to maybe the result can be more than 7 or less than minus 8. So how to handle that result, how to store that result? So maybe we need extra space, extra location, all right, to store the result. So when our system know that arithmetic overflow happen for this operation, so the circuit will take necessary action so that it can store or use more space to store the result. All right. So our job is that to detect or to design the circuit that can handle this problem. Okay. So that is the idea. Now let's now the question is how to detect that arithmetic overflow. So to detect arithmetic overflow, we need to understand the concept. All right. Now we will look at this example. Okay, when the arithmetic overflow happen, and what signal, all right, what signal involved. Okay, so let's look at this. So look at the first example. Yeah, our system is 4-bit. Yeah, remember this. This is 4-bit, and before that, the formula is, or the equation is this. How to know that our system, or what is the range that our system can handle. For example, if or I give you the equation. So the equation is actually this. The negative number for the negative limit is that minus 2 power of n, yeah, minus 1. And the upper limit or positive side is that 2 power of n minus 1 minus 1. Alright, so for example, our system is 4-bit. So what we have is minus 2 power of n 4 minus 1 is 3 until 2 power of 3 minus 1, which is minus 8 to 7. 2 power of 3 is 8, minus 1 is 7. Right? So this is limit for 4-bit. If our system is 8-bit, so you have minus 2 power of 7 until 2 power of 7 minus 1. So the negative limit is minus 1 to 8, and then the positive limit is positive 1 to 7. Right? So this is 8-bit. If 16-bit, use the same equation, so you can get the result, the limit for 16-bit and so on. Right? So this one actually you can, all right, in the notes got this one. So when you refer back later, so here. Okay, so let's go back to this. Now, look at the first case. First case where we have this 7 plus 2, positive 7 plus positive 2. Okay, and the answer should be positive 9. All right, and positive 9, we know that this is overflow, right? Because positive 9 is more than 7 already. Okay, and overflow in computer or digital system, normally we refer as V. V. So this, in this case, V should be equal to 1. All right, means that overflow occur. Okay, and let's see in digital, when we add these two numbers, what happened? Okay, 1 minus 0, you have 1. 1 plus 1, you have 0, and you have 1 carry here, right? You have carry. And 1 plus 1, you have 1 plus 1 plus 0, you have 0. 1 plus 1, 1 plus 1 plus 0, you have 1 0, where this is sum and this is carry. Alright, so you have 0 and you have 1 carry. Okay, and 1 plus 0 you have 1. Alright, so this is the answer. And actually, if we look at this, this is yes 9. Okay, 1001 in digital is actually 9. But remember that our system is 4-bit. If our system is 4-bit, the MSB will be the sign bit. And if sign bit, this indicate or our system will recognize this as a negative number. So actually, if we in logic, right? Because this is positive number, this is positive number, positive plus positive, we should have positive result, right? But we have negative result, means that something wrong actually. Okay, so this we call overflow, arithmetic overflow. So when we observe this, this we call C C2, if we in our adder, right? This we call C3, right? And the carry to the bit number 5 is called C4. This one, this is 0. All right, we don't have carry when we add this number. 1 plus 0 plus 0. The sum is 1, and our carry is 0. The carry C4 is 0. Okay, again I repeat, the operation is this: 1 plus 0, we have 1. 1 plus 0, we have 1, and carry C1 is equal to 0. Right? 1 plus 0, 1. We have no carry. But this one, 1 plus 1 plus 0, we have 1, 0. So 0 is our sum, and carry is 1. Right? So C2, we have 1. 1 plus 1 plus 0, we have 1, 0 again. So sum is 0, and 1 is the carry, and this carry is called C3. 1 plus 0, we have 1, and we have no carry. C4 equal to 0. So we observe that in the first case, when arithmetic overflow happened or occurred, right, and the number is more than plus 7 here, so C4 equal to 0, C3 equal to 1, and we have V equal to 1 in the first case. Now let's look at the second case. When we have this number, the same number, 7, 2, but now 7 is minus number, minus 2, minus 7, and plus 2, and the result should be minus 5, and minus 5 is in the range, right? Remember, our range is from negative 8 to positive 7, so minus 5 is just fine inside this range. So there is no overflow actually. In this case, v should be equal to 0. No overflow. And when we do the add in binary, and this is the process, and remember, minus 7 in binary is this 2's complement of 7. Okay, and see, the sign bit is 1, indicate that this is negative number. All right, so let's do the add. 1 plus 0, we have 1, good. 0 plus and C, 0, right? 0 plus 0 plus 1, we have 1, and C still 0. And 0 plus 0 plus 0, we have 0, still 0. 0 plus 1 plus 0, we have 1, and we have 0 carried. So again, this is C3, this is C4, and our C3 and C4 equal to 0 and 0. Okay, for this case. And look at this. Negative plus positive number, the result can be positive or negative, right? So in this case, negative, so it should be no problem. Okay, so in this case, when C3 and C4 equal to 0, So we have no overflow. Now look at the third case. When this 7 is positive and 2 is negative now. So 7 plus minus 2 or 7 minus 2. Alright, and the result is of course 5, and again 5 is in the range, means that v should be equal to 0, right? So if v equal to 0, and let's observe here. One plus 0, you have 1, carry is 0. 1 plus 1 plus 0, you have 0, and your carry is 1, right? 1 plus 1 plus 1, you have 1, your carry is 1. And 1 plus 0 plus 1, you have 0, and your carry is 1. That's why you have here is 1. Okay, so when we look at this, so this is C3, this is C4. So C3 and C4 both are 1 and 1, right? The third case. Now the last case, which is this. Both number are negative now, minus 7, minus 2. Alright, and the result is minus 9, which is clearly more than minus 8. So for this part, p should be equal to 1, means that overflow occur, right? So look at the operation here. 1 plus 0, we have 1. 0 plus 1, we have 1. 0 plus 1, and of course this 1, we have no carry here. 0 plus 1, we have 1, no carry. 1 plus 1 plus 0, we have 0, and we have 1 carry. Alright, means that here C3, C4, C3 equal to 0, C4 equal to 1. Right? So when we look at this, all of this operation, we can make one conclusion. All right, the relation between C4 and C3 and the overflow or V. So we can have something like this: C4, C3, and V. When 0, 0, what is V? 0, 0, here, here, 0, C4, 0, C3, 0. So V should be equal to 0.
0.
Yes. If 0, 1, C3, 1, which one? This here, right? So V equal to 1. If 1, 0, here, should be V equal to 1. And the last one is 1, 1, V equal to 0. Okay, so when we look at this, the behavior of this, or the relation between C3 and C4 and V, we can observe something here. So this is look familiar. Alright, this is actually an XOR gate, where you can have something like this: C3, C4, and this is V. Alright, this is XOR, XOR behavior. Right? So in conclusion, we can say that to know whether the operation or our adder or subtractor produce V or not, we can use XOR gate. Alright, so in other words, we can have something like this. Okay, so in our for example, in our adder subtractor unit, yeah, maybe something like this. Okay, let's, for example, we have 4-bit adder. Like this. So our adder, we can have something like this, right? These are the input. You can have the C in, and you can have C1 here, C2 here, C3 here, and C4 is here. And this is S, your S sum. Alright. So in order to detect whether our the arithmetic operation produce the overflow or not, simply connect this C3 to this C4 using an XOR gate V. Alright, so if V equal to 1, means that the operation, the adding operation here produce overflow, means that the output, the result here is not correct actually. Alright, so that is the idea. Alright, that is arithmetic overflow. Any question? So if no question, we proceed to the next. Multiplier. Before multiplier, maybe I go to this first. Later we go back to multiplier, because this one arithmetic comparator is related to the overflow or adder subtractor. So last week, we learned how to compare two number, and we can know whether the number is bigger than another. For example, A bigger than B, or A less than B, or even A equal to B, right? Using a comparator. All right, but that comparator, the one that we learned last week, is used for comparing positive number. What if the number is negative? So that comparator cannot be used. All right. So to compare a positive and negative number, and what is used in computer is actually arithmetic, the arithmetic comparator. All right. So what is arithmetic comparator? So we need to understand how we to compare the number actually. All right. So the best way to compare a number is by using subtract. By using subtract. For example, if we have A and B, all right, we want to know whether A is bigger than B or not, or A is equal to B or not, or A is less than B or not. All right, we can do simply take A minus B and look at the result. All right, so for example, if A minus B, the result is equal to 0. So we know exactly that A should be equal to B, right? If A minus B equal to 0, yes, of course, A is equal to B. And if A minus B, the result is more than 0 or positive number. In this case, we also know exactly that A must be greater than B. Alright, because A minus B is positive. Alright, no need to know what is A, what is B, but if we take A minus with B and the result is positive, then for sure A is greater than B. And if A minus B, the result is less than 0 or negative, means that the only thing that value of A and B is that A must be less than B. Alright, because A minus B, we have negative. Okay, so in conclusion, we can use adder or subtractor, in this case subtractor, to be our comparator. Just look at the sign of the result, whether positive or negative, or whether it is 0 or not. Alright, so if the result is 0, A equal to B. If result is positive, A greater than B. If result is negative, A less than B. Alright, so you see, with adder, now you can have, with one circuit, adder, you can have, yes, of course, the adder, and you can have the subtractor using the same adder, and now you can have a comparator also using the same circuit. Alright, so we can have something like this to create a comparator. Okay, look at this. So this is the adder, full adder, 4-bit, and we have x. X is one of the input, and y. When we look at y is the complement here before we do the complement. Alright, because we have not gate here. Alright, so meaning that what go to y is that y3 bar here. This one is y2 bar, or the complement of y2, y1 bar, and here is y0 bar. And look at the input here, 1. So what you have actually? You have second complement of y, right? Plus with x. Means that the operation here is actually x minus y. Right? The output s, s here is x minus y. Why? Because y that enter the full adder here is actually the second complement of y. Why second complement? Because you complement y here, right? From y3 you have minus y3 bar, and you add with 1. Add with 1 here means that second complement. Alright, so s is actually x minus y, so this is subtractor actually. Subtractor, and we see that this one is connected to, or can be used to check whether the number is positive or negative. Okay, so if s3 equal to 1, means that the result is negative. If the result is negative, means that x less than y for sure. Alright, and if the result is 0, s3 is 0, means that x is greater than y for sure. Right? Not sure yet, right? Because if 0, we need to check another one. Right? If s3 equal to 0, not sure yet whether x is greater than y or not. Can be something like this. X equal to not equal, x equal to y, or maybe greater than y. So you need to check whether x equal to y or not. So how to check? Easy. You check whether the result is 0 or not. So how to know that the result is 0 or not? So you need to make sure that this one equal to 0, S2 also equal to 0, S1 also equal to 0, and S0 also equal to 0. Means that x equal to y. Okay. So if all of these signals are equal to 0, go to this NOR gate 0, 0, 0, 0. What happened to this signal? The output should be 1. Alright, NOR gate, remember? Or if all are 0, so the output should be 1. Alright, if either one, for example, either one you have 0, 0, 1, here the output should be 0, always 0. If either signal here equal to 1 or more than one signal here equal to 1, the output here will be always 0. But if all signals are equal to 0, the output here z 0 is definitely 1. Alright, so if this we check if equal to 0, yes, maybe x more than y, but we need to check this also. If this equal to 1, means that yes, x equal to y. Alright, but if z equal to 1, if z equal to 0, 0 means that you have the result here. Either one here should not equal to 0. Alright, if this is the result, yeah, this is 0 and this also 0, definitely x more than y. Okay, so that is the idea, and we have another one to check whether overflow or not, which is we, using the XOR gate and come from C3 and C4. Alright, so when we compare this comparator with the previous one, so this one is a lot easier, a lot easier. Right, and of course you save the cost a lot, right? Because you don't need to have another circuit. Alright, now you have one kind of circuit which is an adder. You can create adder to do addition, and you can also can use to this circuit to do subtraction, to subtract, and also you can use the same circuit to compare numbers. Okay, so that is the idea. Alright, so before we go to multiplier, any question? Now we look at multiplier. Okay, how we create a multiplier in hardware. How to multiply a number in hardware. And again, we need to understand, or we need to know how the multiplication is performed in binary, right? And of course in human interpretation, how we perform multiplication on paper, right? So this is how we do multiplication. So for example, if we have two numbers, and the first one we call it multiplicand M, and the second number we call it multiplier Q, and let's, for example, the number is 14 and 11, and when you change to binary, 14 is 1110, and let's say this is a positive number, a positive number, all right? And 11, this is 11 in binary. Okay, So to multiply, of course, you take this multiplicand and multiply with the first digit of the multiplier. So you have 1110 multiplied by 1. Of course, you have the number back 1110. And again, next one, you multiply the multiplicand with the second digit of the multiplier, which is this one. Yeah. Can you see the cursor? No. Alright, this is okay. Again, I repeat. So when you have the number 14 and 11, so this is in binary. Okay. When you multiply these two numbers, so the first multiplicand, you multiply with the first digit of your multiplier. So this multiplied by 1, you get this. And multiply by the second digit of the multiplier, you can get this. And you multiply this with the third one, which is 0, you get 0. And multiply with the last one, you get this one. And you get this. You have 0. And this you add 1 plus 0, you have 1. And this you add 1 plus 1, you have 0. And you have carry and plus, and you will have this. Yeah, this, and this is 154 in decimal, and of course 14 multiplied by 11, you have 154. And this is how you do multiplication in binary. Okay. And the good thing about binary is that, yeah, you just only multiply by 1 and by 0 again. So by 1, you get the number back, and by 0, of course, you get 0. So the multiplication is easy actually. Okay, but that is on paper. On paper. How to implement this in hardware now? All right. Because remember, we not implement this on paper. We want to do multiplication in hardware. We want to implement this multiplication process in hardware. We want to create the hardware to do multiplication now. All right. So in hardware, we need to think how to make it easy. All right. So when we observe this, yeah, we can see that we do this multiplication and we add. And multiplication is simply just like, because when we do multiplication, for example, this one with 1, it looks like we do the AND operation. AND operation, right? 1110 multiplied by 1, same as 1110 AND with 1. Where you AND with 0, you get 0. You AND with 1, you get 1. Right? So you can use AND gate for this operation. Alright? And again, here you want to add. Add this to this, add this to this to this, means that you can use adder. Okay? So now, in hardware, to multiply number, you can use AND gate and adder. Alright? Okay, now, in hardware, to do this add 4 times like this is difficult. Alright? Difficult. So, what we can do is, we add 2, and again 2, 2, because we have adder, where we have something like this, right? A, B, and we have output, 2 input and output. We can add 2 numbers. But before this, we're not adding, or we don't have adder with many input like this, A, B, C, D, and get result. No, we don't have that. So we can use two input adder and modify this a little bit to this. Alright, so what we do is, now, yeah, do the same process, but now we, for example, this one, multiplicand, we end with this one to get what we call a partial product 0, which is simply this and with this, and we get 1110, the same with this one. And we end again this one with this the second digit of the multiplier, this one, and we get the same number, right? Same as this one. But instead of we multiply or and again this one, we add first. Yeah. Use the adder, two input adder. We add this number. Alright, 1011 is the product of this addition. This add to this. And of course this one no need to add, right? Go straight to the result. So this one go to the result. And this one we add, so we can get this number. Alright? And this we call partial product 1. And the third multiplication, third digit, is multiplied by 0 with 0. So we have 0, and again we add first. We add here, we get this, and this one will go to this, right? Same as this one. This one plus this one go to this. This one also the same. This one plus this one, get this and go to result. And this one we add, we get what we call the partial product 2, and again we add with the multiplication of the last digit, which is this one to this one and this one. So here you can see we use one adder. Here we use another adder. Here we use another adder, and at the end we can get the result. The result of this multiplication. So that is the idea. If this is the idea, then we can produce the hardware to do this. Right? So now the process is like this. Now we change the number to variable, right? So now in variable, okay, let's for example still 4-bit here. The first digit we call it M0, multiplicand. All right, M0 bit, the first bit. Second bit M1, M2, M3, and the multiplicand Q0, Q1, Q2, Q3. And to get this, is by AND this one 0 with this one. So what we do is M0 and this is AND operation Q0. For this one, M1 and with Q0, you get this one. M2 and with Q0, you have this one. M3 and with Q0, you have this one. And of course, this one straight to the output, which we call P0. Alright, same as this one. Alright. Now, this is partial product 0. Now we want to get this one. So this one how to do? Which is M0 Q1, M1 Q1, M2 Q1, and M3 Q1. Alright. And again, this one we use adder. Here we use adder to add this to this. And we have this is partial product 1 bit, the first bit, and go to the output. Alright, this one add this one, this one add this one, you get this, and this one you get this. You add with 0, nothing here, you get this. Alright, and this one, this from same as this one. Alright, the carry and so on, same as this one. Alright, so this is actually the carry from this plus this one. You have this one and you have the carry, and this one is just a carry from this operation. Alright, and the rest should be the same process. So in hardware, we can do something like this. Right? So let's change that to the hardware. Now, let's look at this. How to do M0 Q0? M0 AND with Q0. So this is how you use AND gate. M0 n with q0, yes, you have p0. All right, very easy. M1 q0, you have this. M2 q0, you have this. M3 q0, you have this. And you want to add with what? You want to add with M0 q1. So this is M0 q1. All right, and you add. You use full adder. You use full adder, and you have P1, exactly this one. And this one also the same. M1 Q1, which is this one, M1 Q1, you add with M2 Q0, this one exactly, for this one, and also this one, and also this one, same as this one. So in conclusion, we use adder to do multiplication. All right, so you see, actually in computer, whether you want to do add, you do sub, you do multiply, and actually you do division, you will use the adder. But if division we not cover in this course, you can go back and check on the internet how we do division. All right, so that is the idea. All right, now how to design the circuit, and this is big, right? That's why the multiplier is costly, very costly, because you see, when you want to multiply a 4-bit number, all right, 4 by 4, so how many adder that you need to use? How many? You need to use 1, 2, 3, 4. 4 by 3, you have 12 adder. 12 adder for 4-bit number, and the result is 8-bit. All right, the size of the result is double of your input. Okay, so if you have 4 input, one 4 input, another one is 4 input, so the size of the input is the total bit, the size of the input. For example, 4 by 4, so the output is 8. 4 by 2, the output is 6. 8 by 8, the output is 16 bit. All right, so the adder is expensive. Now the question is how to design this. It looks complicated, right? But again, although it look complicated, but you can see here that actually the pattern is again repeated. This one is actually the same as this one. You see, the pattern here is actually the same with this one, and also the same with this one. So you can use the hierarchical design methodology, where, all right, you create this module, and of course we have learned already how to create this kind of module, right? Last week in the tutorial also we create the adder subtractor. The structure is similar to this, right? So we can create this to make a smaller module, or to make a module, all right, to make one module, and then we connect this together like this. All right, like this, where inside this is the same circuit, and now we can get the bigger module, the 4 by 4 multiplier. So for this, I really encourage you, all right, to try to create the Verilog code for this one. All right, this is very interesting. If you can do this, then the outcome for this course is achieved for chapter 3, 1 to 3 already, if you are able to do this. All right, okay, try, take your time to try to do this. Actually, you can do this. If you can do this, then should be no problem for this. All right, we can discuss anytime. All right, we can have one session, for example, using WhatsApp, or maybe you Google Meet if you want to discuss about this. All right, so that will be the multiplier. Any question? Okay, so if you not understand uh, uh, the concept, maybe you can refer back to the video later on. Yeah. All right, so we want to go to the last part of this. The last part will be the ALU, or arithmetic logic unit. Yeah. So this is the ultimate target when we design a combinational logic. So we want to design a brain of the computer, which is the ALU. So the brain of the computer is actually the arithmetic unit and logic unit, of course. So how to design that? So actually in the ALU, all right, for any microprocessor that we have today, all right, contain the operation like this. This is a small one, small scale one. So we have, for example, we have how many operation here? So the ALU can do, for example, in this case, can do 8 operations. So the first operation is a plus operation, yeah, where the input of A and B. All right, when we have A and B, and we have one control signal, we call it operand, in this case OP, and the size is 3-bit. Why 3-bit? Because you have 8 operation. Okay, if you have 4 operation, 2-bit enough, right, to represent all the operation. Okay, so in this case we have 8 operations, so that's why we have 3-bit control signal. In this case, the control signal is called operand, or in short OP. And this is the symbol of ALU. If you look something like this in digital, this is the ALU, right? So the ALU, normally we have 2 inputs, A and B, or X and Y, or whatever, but 2 input. Right? In this case, is the size is 8-bit. All right. Actually, change a little bit. 8-bit is should be 7 to 0. All right. Mistake here. 7 to 0. Yeah, 8-bit. This is 9-bit already if you start with 8 to 0. Okay. So we have 9-bit, 8-bit. And this ALU can perform many operations. So these are the operations. All right. So if the input of the operand or the control signal is 0, 0, 0, so the output S here will be A plus B. All right. If the operation here is 0, 0, 1, the output here is A minus B. If 1, 0, 1, 0, we compare A and B. If 0, 1, 1, we multiply A and B. So the output will be the multiplier. So this should be, again, if multiplier, this should be 15. If we have multiplier, so cannot be 8 already. So we have 15 to 0. All right. So this should be 15 to 0. Okay. Size, and we have Z and C, and another one is V, actually. V, and when the operand is 1, 0, 0, is the logic operation now, A and B. The output of this is A and B. All right. So if 1, 0, 1, so we have A or B. If 1, 1, 0, not B, means that not B only. And the when the input is 111, OP here 111. So the output is pass A, means that A from here will go to S, pass A. Okay, so this is just an example of ALU. So you can have many kind of ALU that has, for example, only 4 operation, or you may have more than 8 operations. So depend on the design. So for example, in the CPU that we have today, yeah, the operation is much bigger, right? Because this microprocessor can do more operation. Yeah, so this is just a small ALU. Yeah, so when we look at this, yeah, how to design an ALU? Okay, so first thing is that we can design A plus B using adder. We can also design A minus B, which is the subtractor. We can design a comparator, A compare B, which is the same circuit actually, right? Add, sub, and compare is actually using the same circuit, right? And multiplier, we learned just now that we can design a multiplier. All right, and of course the multiplier is the big one, the most costly one. And A and B, yes, we can have A and B. All right, and we have A or B, we have not B, we have pass A. And how to get this control signal? How to do that? The answer is to use the multiplexer, right? So okay, we have the multiplexer to design an ALU. So this is extra from the notes, because here you don't have the design but only the symbol. So now we want to design the ALU. So to have this, all right, you can use a multiplexer. So what is the multiplexer? Should be 8 to 1 multiplexer. All right, so you can have something like this. Big multiplexer, just like that. And you have the control signal. This is called OP, and the size is 3-bit, right? Operand. And you have, when operand is 0, 0, 0, you have add operation. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Right? And you can have the output here is the S. Yeah. So for 0, 0, 0, 0, 0, 1, 0, 1, 0, when we look at here, this tree is the same circuit actually, the add sub circuit, right? So you can have the something like this. The add sub circuit, right? Okay, and this can be A, and you can have B. All right, so if 0, 0, 0, so the operation should be the uh, the add, right? 0 0 0 should be add, and 0 0 1 should be sub. So you can have another signal here is sub, add sub that we learned last week. All right, and this one can be can connect to the OP as well. So we will you need to do that later, right? But in this case, just the idea, and the output for this one is should go to the this also. All right, and also yeah, when 0 0 0 1 0 0 1 0 is also the same, should be no problem. Use that one. And for 0 1 1 is multiply, so you need to have another circuit, which is the multiplier. Right, cannot use the same circuit anymore. So in this case, you need to have a multiplier. So this is multiplier. So again, this input is A and B, right, and the output is go to 0 1 1. Okay, and for 1 0 0 1 0 0 is A and B, so easy. So you can have AND gate for this one, which is A and B as well. And for this one, 1 0 1 is OR, so you can have OR gate for this one. OR gate for 1 0 1, and not B. So B, this is B, not for this one, and the last one is pass A. So just get the A signal and send to this one. You have pass A. So the circuit is looks like this. Looks like this. Okay. Right. So this is an example of ALU circuit. All right. Where you see when the OP is 0 0 0, so the output S is from the adder. All right. When OP is 0 0 1, the output is from the adder also, but with the add sub signal here, we set to sub. All right. So the output is the subtract. All right, the subtract. And when 0 1 0, the output is from this also. All right, and of course here you need to have the flag. The flag should be from the adder subtractor unit. So here you need to have N, you need to have Z, and one more is V. All right. So the output for the comparator is this one. So 0 1 0 is no need to go to multiplexer, also no problem, because the output is here. All right. And when 0 1 1, you get the output from the multiplier, and 1 0 0, you get the output from the AND gate. All right, because 1 0 0 is AND operation. And for 1 0 1, you get the output from this, the OR, and here you get the output from the NOT, and last one you get the output from A, right? Because pass A, just send A to S. All right. So that is the idea of the ALU. See, when we learn the multiplexer and we learn adder, subtractor, and the comparator, and we learn the multiplier, and of course we have another one which is the divider. Actually, we can use multiplier also, the same circuit, and to do division. And we learn how to manipulate the logic also, and or XOR, or not XOR, or whatever gate. All right. So this combined together with this multiplexer, we can have an ALU, all right, arithmetic logic unit, which is a very important circuit in microprocessor, or in other words, in your computer, right? Okay, so that will be chapter 3. Okay, so any question?